Я очень рад возможности сегодня здесь выступить. Большое спасибо за приглашение. Меня зовут Колесников Саша. Я студент в группе Кристалла. И мы находимся в австрийском институте, который называется ICT. Когда я готовил эти слайды, у меня были сомнения, на каком языке их сделать, на русском и английском. Вот. И я понял, что большинство терминов я не могу перевести на русский нормальным способом. Поэтому я буду говорить сегодня по-английски. So now I'll switch to English. So I will talk about deep learning and weakly supervised image segmentation. So here is a general outline of my talk. I will start from a short introduction into semantic image segmentation. In particular, I will explain how you can do fully supervised learning for image segmentation and what is weakly supervised learning for image segmentation. And then I will explain my recent project. So I proposed a new method for weakly supervised image segmentation. And the paper about this was just submitted to arXiv. It appeared on Tuesday, so you may look this paper afterwards if you want. And then I will present some experimental evaluation and in-depth discussion of what's actually going on. So before going to segmentation, I would like to remind you how we can use deep network for classification. So that's, I think, the main reason why deep network initially became so popular, because they have this remarkable property that they can solve image classification problems with really high accuracy. So the main idea of deep learning techniques is that you have a series of convolutional layers with unknown parameters. And yeah, I forgot to say that I think I don't have material for 90 minutes, so if you have any questions, feel free to ask. I think we'll have enough time to address your questions. So yeah, how many of you are actually familiar with deep classification networks? So roughly half, right? Okay, so who is not familiar with deep classification networks?
Come on. He's familiar.
Okay, so you may use standard networks such as AlexNet or VGJ to solve the image classification problem. So essentially, it's just a series of convolutions, and then in the end, you have one or two fully connected layers, and then you make predictions. So, and you can use similar architecture to solve image segmentation. So the only thing which you do, you just don't add fully connected layers to the end. You just use convolutional layers as a image segmentation. So it just looks like this. You have many convolutional layers, and then you basically treat last convolutional layer as your segmentation. And if you have fully annotated data, you can easily train this network using standard backpropagation technique and obtain quite good results. So generally, like one of the popular pipelines for semantic image segmentation when you have full annotated data looks like this. So you first train deep convolutional network in a fully supervised way, and typically it produces a segmentation mask which is smaller than original image because you often have this max pooling and subsampling layers. Then you use simple interpolation to match the original size of the image, and then you may improve this segmentation using standard CRF techniques and obtain increased segmentation masks. So here are a few examples how segmentations produced by recent deep networks look like. So as you can see, they look quite good. So yes, in case when lots of full annotated data are available, you can train really good models. But the problem is that if you want to produce segmentation mask which looks like this, manually. It may take 5-10 minutes depending on how complicated the image is, and you need at least 10-20,000 of these images, so it's quite costly and hard and not always feasible to do this. So that's why people consider bigger supervised approaches for training segmentation neural networks. And there are many different settings in bigly supervised world, and I will consider one particular setting, which is, I think, one of the most challenging and interesting. So in this setting, we don't have full segmentation masks for our data, but we have only per image labels. So let's say for this image, we know that there are sky, building, and tree on this image. And then given only this data, we want to learn how to segment these images. So that's the setting. Is it clear to everybody? Okay, now I want to discuss. So, yeah, I want to say that it's kind of recent setting, and people didn't really consider it like maybe 4 years ago because it's too complicated. And now with deep networks, it's actually manageable to do something which doesn't look random. So before people tried to do something with just this data, and segmentations just look slightly better maybe than random. And now with deep learning, it's actually possible to do something which is better than nothing. And I want to go through a few recent approaches which were the best on the recent ICCV conference. So one approach is actually multiple instance learning. So the idea is that you can see the convolutional neural network which outputs segmentation masks. So one mask for every class. And then, unfortunately, if you have output which is just segmentation masks, you cannot really train this network because you don't have these segmentation masks. So the idea is to collapse these masks somehow into a single segmentation score. So if you have a segmentation mask for, let's say that this is a segmentation mask which responds to dog, and you can see that there is no scores which are high, then you actually make collapse and say that there is just no dog on the image. So we just have one score for this segmentation mask. Or for this segmentation mask which responds to cat, you actually have some signal here, and you collapse it to some non-zero score. And then you can actually, you have a supervision for these kind of scores. So you know which classes are there, which classes are not there. So, and then you can use standard classification laws to train this network.
Binary classification.
Yeah, just binary classification for every class. So depending on which problem you solve.
And how it collapse? Just average on.
There are many ways you can do this, and I actually will come back to this later. So the most prominent ways are to take maximum, so the maximum response for each mask, or you can take average as well, or there are other approaches. And I will also propose a new approach for this. So yes, actually, you don't really have any guarantees that network will learn something reasonable. It doesn't have to. It just has to somehow, if there's cat here, it has to put cat somewhere here. It doesn't have to put exactly where cat is located. So there's no like theoretical reason to do this. But in practice, I think it's easier to explain image in the right way, so it works somehow, this approach. The other approach is...
should we pre-train this network?
Yeah, I forgot to say that networks are always initialized from standards network training image network with VGJ, but it's not networks. So another paradigm for training image segmentation models from just labels is so-called self-training. So the idea is that you use output of neural network as supervision, but you modify this output in a way that the output is consistent with big labels. So you start from some random deep network. It may produce some random segmentation mask, and then you try to basically find the closest segmentation mask to the one which the network just have outputted, which is consistent with labels you have. So network may hallucinate any classes on this image, but then you basically forbid wrong classes and encourage right classes to appear on the image. So and then you basically modify this in this way the output, and then use it as supervision to neural. So again, there is no guarantee that it will work in practice, but so people actually have shown that it converges to some reasonable results. And the last approach, which is called constrained CNN. So even though it's formulated differently, it's actually really close to this approach. So initially, the problem is formulated as follows. So Q is the output of the neural network for every image. So for every image in your dataset, you consider the output of the neural network, and then you can encode weak supervision. So you have this weak supervision which says which labels appear on which images, and it's quite easy exercise to encode this supervision as linear constraints. So you take the output of your neural network and you use linear constraints to constrain the output to be consistent with your weak supervision. And this Q basically depends on the parameters of your neural network. And then you just say, okay, I want to find parameters such that these constraints are satisfied. And this is an extremely challenging problem, and I think it's just intractable to solve because this is inside it has a deep neural network, so it's very non-linear, non-convex constraints. So there's no hope to solve it. So the authors of this paper propose to consider relaxation of this problem. So they say, so they introduce a latent variable p, which is basically new segmentation. So p is basically segmentation for every image in your data set. And this, they say that p should satisfy the constraints which we have. And we want to find parameters of neural networks such that they're close to p, and p itself is a basically segmentations which satisfy the constraints. So by introducing some latent variable, you actually make the problem easier. So you want the output of your neural network to be close to something which is actually consistent with your weak supervision. And then they basically propose to fix theta and optimize for p, and fix p and optimize for theta. And then basically if you think what actually is going on, you may see that just exactly the self-training as I showed you in the previous slide, but actually the steps are very similar, but just the details are different. So you can put any metric here, and they use scale divergence, but you're free to put any other metric and then invent many new methods. But essentially it's just, so the idea is to use output of neural network, which is projected somehow to satisfy weak constraints which you have, and then use this projected output as supervision. Yeah. Am I speaking too fast? Or?
Does it produce any feasible? Does it produce feasible solution for any training image?
It doesn't have to, so it's I think simplified formulation, and the final formulation which also they also have some slave variable here, so they allow to violate some constraints, and they also add slave variable here, so they penalize for violation.
And how to construct the p value?
So p is just a latent variable, yes. And initially initially you initialize theta randomly, then you compute q, and then initialize p to be equal to q, and then you start this block coding optimization process. So p is essentially a segmentation mask. So it's a huge variable which has a segmentation mask for every.
But in this case, p is not feasible if it's equal to q.
Yeah, I think it doesn't have to be feasible. So
okay.
I'm not sure about the exact optimization procedure, but it's I think quite simple problem. So when you fix theta, It's just the context optimization problem.
Yes.
And if you fix P, it's just the problem for which you have closed form solution. No, not closed form, we use backpropagation to update the parameters. So if you fix P, you basically just have ground truth and you train Q to match this ground truth. Just single backpropagations. Okay, so that's all I wanted to say about the related work. Now I will go to the method which I recently proposed. Okay, so don't try to immediately understand what's going on. I want just to give you general overview of the proposed approach. And then I will go step by step and explain every single component. So, okay, I start from an image for which I know semantic labels which appear on the image, which is person and cow. And then I use standard convolutional neural network to produce some segmentation mask. It can be random in the beginning. And I basically have three guys, three loss functions, and each loss function accounts for certain aspects of weakly supervised image segmentation. And I optimize some of these loss functions. And this is basically standard end-to-end trainable architecture. So these gray arrows indicate the flow of gradients, so everything is differentiable here. So it's just a standard feed-forward network. And in the next few slides, I will explain every component one by one. Okay, so first component is localization loss. And I want to go back to the classification problem for a moment. So as you know that we can solve classification problems quite reliably with convolutional neural networks. And so you may actually try to ask neural network if it predicts that there is a bolt on this image. You can try to dig into it and try to understand why it thinks that there is a bolt on the image. So you can use classification networks to somehow provide weak localization cues on the location of the object.
Можно вопрос? Это как в оверфите мы пирамиду масштабов используем для того, чтобы сегменты генерировать? Мы на одном масштабе это делаем или на многих масштабах, как в оверфит? Ну вот это вот в классической постановке мы сделаем свертку с разными классами, которые представлены на данном изображении с помощью deep learning. На одном масштабе или мы используем?
Just a single scale. So don't use any multi-scale tricks. Just one deep neural network and just single scales. So I think if I use some tricks for multi-scale classification, then it will improve it. But I just consider simplest case and just like a single scale and single neural network.
Спасибо.
And here's like general idea what's going on. So I assume that I have trained neural network to predict object categories. And then there were actually many recent works which suggest how we can use classification network to extract some localization cues about object locations. So here's just an incomplete list of these works. And yeah, generally it looks like this. So if you have a person here, most likely neural network will identify that there's a person on the image. And if you try to understand why, you will most likely find something which looks like this. So neural network just recognizes the head of person. It doesn't care about any other stuff, and basically doesn't give you full segmentation, but it gives you quite good idea where object can be. You can do the same for all classes, including background, and then typically people who propose these methods, they also propose a mechanism for thresholding these segmentations, produce some reliable parts which you can, so you can expect that this should be right localizations. And then I produce these big localization maps. So it basically says that the cow should be here, person should be here, background should be here, and it doesn't care about everything else. So it's just, it doesn't suggest any semantic labels for the other parts of the image.
background is a class or
Yes,
some?
it's also considered as a class.
It's a class and trained on neural network. On you say you pre-trained on ImageNet, but what is the background in this property?
So to initialize the network, which I use the network between ImageNet, but the actual data set is the other data set. It's Pascal VLC. I will say a few words about this data set experimental section. So, but yeah, in Pascal VLC, background is a just proper class. So, but it basically appears on all images. So on all images you have background. So, and you have to predict it.
You trained your deep network on Pascal and use and trained this class. So you have 21 class.
Yes, I have 21 class including background. So yeah, I don't want to explain all these methods, so they're quite technical. But I want to give you an idea how it may work. So I will consider maybe the first one and the simplest being suggested by Simonian. So yeah, at this point I will introduce some notation. So let's say that X is an image. Y is a segmentation mask, which is just a collection of discrete labels. And yeah, let's say that I train a neural network F, which takes image as input. And so for every location, for every image X, for every location U, and for every class C, I want to model conditional distribution of C in label C at position U, even X. So that's how neural network is parameterized to produce these conditional distribution. And
It is absolute position in the image. It's not.
So it's just some abstract position in segmentation mask. So you need to refer to a concrete architecture to explain what is it. So essentially, segmentation mask is typically smaller than the original image, and it has fixed size. And then instead of just considering two-dimensional coordinates, I collapse it to one coordinate. It's easier to write. So it is just some positions inside segmentation masks which are produced by network.
But here you can learn just position and training image set. You learn position that cow is up, person is down in an image, bottom of the image. You learn positions in training set, or it's.
So positions are not given to you as input. So neural network just takes X as an input. So just sees some. So basically, just sees some part of image, and then predicts for this part what actually is there, but it doesn't know the position. You may also add the position as feature. It won't hurt. So you may learn that person is on a cow is located like bottom of the image. But I don't have positions as features.
Okay.
And you may also have a neural network F, which predicts class labels. So it's just for every image X, predicts label C. So the question is, can I use this network to produce some weak localization maps? And there are many ways to do it. And the simplest way is perhaps to use a normalization trick. So if you have differentiable function, by definition, it means that you can approximate it locally around X as a linear function in X. And W is essentially gradient, which you can compute using standard Lie propagation. So you compute a gradient with respect to input image for some plus C. And then basically it says that this weights vector basically says how each location of X influences locally the final score. And if you draw this mask, they will look like this. So for each class, you do this linearization, and then you draw this vector W, which has the same shape as X, and X is 2D image. And then it will look like this. And yeah, you may also consider other approaches which actually provide better results. And I use this recent CVPR paper in my experience. But I won't explain now how it works. It's not very complicated, but a little bit technical. Okay, so let's assume that we have this peak localization step fixed, which was trained on just per image labels. And then I just use simple classification mask for every pixel which appears in this segmentation mask. So I basically penalize network for being not consistent with this big localization cues. And I think so. Yeah, the main trick is that you don't try to produce full segmentation mask to guide the network. You just use some small regions to guide it, and don't penalize it for doing anything on other regions. So that's the first part. Now I'll go to the second part of levels. So here I basically use the standard multiple instance learning approach. So I use network to produce segmentation mask, and then I collapse segmentation mask for every class using some aggregation technique to produce classification scores, and use these classification scores inside standard classification laws. So for every class I have a binary classification problem, and I use the standard classification laws to enforce this consistency. So the question is how we should collapse this segmentation mask into just single score. So any ideas how?
Use a maximum function. Use a maximum on each.
Yeah, maximum is one approach. So the problem of maximum is that it just encourages neural network to find one location where an object is. And you typically will have really small segmentations. You can go for average pooling, which basically encourages all locations to be high, and then you will have two big objects. So here basically I show you examples of how global max pooling and global average pooling look like. So basically this is the input to global max pooling. Then you may interpret global max pooling as producing this mask with just zeros everywhere except for the position of maximum. And you take inner product of these two matrices. Average pooling looks like this. You just fill this matrix with these uniform weights and do again this inner product. And then, as I said, this pooling strategy is not perfect because it encourages only one location to be high and doesn't care about all other locations. So you most likely will miss some big parts of the object. And this thing encourages everything to be high, so you will have huge objects, and which is also. So the idea is to somehow propose a method to interpolate between these two behaviors. And yeah, I call it global weighted rank pooling. So the idea is that it's basically weighted average, and weights depend on parameter which I call DC. So it's basically decay rate. For every class, I may have individual decay rates. And let's say if it's equal to 1/2, then so the highest activation will have weight 1. The second highest activation will have weight 1/2. Then the next will have weight 1/4, and etc. So here I have, in my example, I have decay rate equal roughly. And you have to normalize these weights so they sum up to 1. So here you normalize by 2 weights, so they sum up to 1, and you will have a mean weighted mean function. And it's also important that you care more about high activations. So you give higher weights to more promising locations, and this way you, depending on parameter D, may encourage some fixed fraction of an image to contribute with some fixed weight to overall score. And if D is equal to 1, you actually recover average pooling, so all weights are equal. If D is equal to 0, you recover max pooling. And if D is somewhere in between, you may recover some intermediate behavior. So in principle, you may want to set this parameter individually for every class and for every image, because sizes are different, and like on every image, every class may be in different size. But in our set, we don't actually have knowledge about this size. So we just set them to some reasonable parameters inspired by the constants which people use in literature in similar settings.
If I just normalize input, and it's a big difference.
What do you mean normalize input?
We need to sum this matrix to be 1. And we normalize sum of all elements, L1 normalization to this matrix. We have a close decision to weighted rank. Мы не присваиваем самому большому числу какое-то значение, типа там от единицы, 1, 2 или еще, а просто нормализуем, и у нас будет самый большой и останется самым большим. Ну, это такая тоже простая идея, насколько она сильно отличается от того, что мы присваиваем какие-то коэффициенты отранжированным элементам матрицы.
So if I understood you, so in your case, imagine that all values are equal, then you essentially average all of them, right?
Нет, я нормализую матрицу. Просто вот если мы оставляем, что вот, допустим, сейчас самое большое число 7,7, ну, как оно и останется самым большим, если мы просто поделим на сумму всех элементов. Просто насколько сильно это будет отличаться от того, что мы присвоим какой-то заранее заданный коэффициент числу победителя. Ну и, соответственно, будем присваивать. Это сильно отличается?
Очень похоже. It seems like a dot product between the original mask divided by average on this mask. Right? То есть ты предлагаешь взять матрицу подмену, поставить ее как вектор, умножить на нее же, то есть скалярное произведение, и поделить на сумму матрицы.
Ну, где-то так же.
Just first normalize and then multiply, but suggest to first multiply and then.
Ну ладно, давайте дальше.
Once you fix the parameters, it's again linear, but let's discuss later. This the final value. Yes, essentially. So here I have just some random constants, but in my network I have probabilities here, which are normalized from 0 to 1, and then you have something from 0 to 1 after you do this. Yes, for every class you produce one probability, so it's basically applied on per class level. For every class you have segmentation mask, and then you collapse the segmentation mask somehow to one probability. Yes, exactly, but we don't have ground truth for every pixel, but our network produces these ground truths, not ground truths, this segmentation mask. We don't know how to train this segmentation mask directly because we, as you said, don't have ground truth. So we collapse this segmentation mask to one label, just to one score, and then we have actual label for this score. And it's basically indirect way of training neural network segmentation. We cannot train it to produce some segmentation masks, but we can train to produce this single score. And then we hope that this segmentation mask will actually make sense as well. So, yes, and as I said, I don't know how to set this constant d for every image and for every class because I don't know the sizes of objects. So I propose just simple rule, and I say that for all classes which present in the image, I use constant d plus, which in practice is I think 996, which corresponds to the fact that 10% of image iterations contributes 50% of the overall score. So just some simple rule of thumb. So I think if you want to try some other constants, results can be better. So for classes which are not in the image, I use d minus equal to 0, which basically says that if class is not in the image, I'm happy with max pooling. So max pooling just discourages any appearance of the class on the image. And I also have one constant for background because background is a special class which is typically bigger than all other classes and appears and it's typically big. So for background, and also have a simple rule. So these parameters were not tuned because I don't really have a segmentation mask for my validation. I have them, but I'm not allowed to use them directly to my parameters. So I just made up these parameters and they work better than just average to the max. So some intermediate behavior with some stupid parameters that look better than.
Isn't it like you train the network always fine only one instance? For example, we have several people in the image, but if you fix the parameter like about size, normal size of the person, it will always find one person and stuff.
Well, it kind of has lots of freedom, so it's so it doesn't have to basically find some fixed size. So I mean, it's encouraged to match some characteristic size, but if you go bigger or smaller, network the loss won't be too sad. So and I have also other losses which compete with this loss. So it basically gives the idea, like very general idea, that object shouldn't be too big, too small. It allows for large deviations, but of course I would like to have these constants like for every individual image and for every individual class, but I don't have that. So yeah, but if you actually have some more clever procedure to set these constants, maybe some additional image prior to guess, and that would be cool. But like, for now, I just have 3 constants for classes which are there, classes which are not there.
I mean, we could separate. For example, we have 2 person.
Yeah, actually, I don't know. I just have one label for image. There are like many people on the image. I just still know that there's a person there, maybe one label. So it's not any data. I just know that either something which looks like person is there or not. Okay, and that's basically everything I want to tell about the second component, and now I will go to the last component, which is boundary variables. So in this component, I use conditional random fields. So who doesn't know what is conditional random fields? Not so many. So essentially, conditional random field is a tool to model probability distributions of many labels jointly. And you may consider segmentation mask as a collection of as a big collection of labels. And with CRF, you may model the probability of these labels jointly. And you can also take into account pairwise interactions. So if you know that two pixels are close to each other and they have similar color, you may actually introduce some prior knowledge that close pixels with similar color should have similar label or the same label. And basically CRF allows you to formally write this down and then make an inference procedure. So you start from some vague segmentation mask, and then you use this segmentation mask and the image to construct a probability distribution, which tries to, first of all, respect your current beliefs, and it also tries to respect some pairwise structure of pixels in the image, and produces a new distribution, which hopefully will respect the boundaries of objects.
Is it fair to say that CRF in this model mimics like properties of objectness separators, like algorithms that detect separate objects based on some heuristics, and tries to mimic the distribution based on a result of segmentation? I mean, like you said that edges, it can separate objects one from another by correlations in pixels and small region, local properties, masks. So is it fair to say that it's object prior of some sort?
Yes, it's exactly basically segmentation prior. So I use some segmentation prior to improve segmentation. But as far as I know, it's quite non-standard use of CRFs for training deep neural networks. So far people use the CRF to improve the output. So you first produce some output, then you use CRF to improve it, and then you basically, the loss function comes after this.
And the CRF is defined on a pixel basis or superpixel basis?
Pixel basis. But yeah, so there's small remark that this network produces segmentation masks in practice of size 40 times 40. So basically, I downscale this image to match this size. So
to be computationally tractable.
That's not the reason why I do this, but it helps to be much faster. But the reason is that I just have small segmentation masks. So that's all information I have. So I free to downscale image, and I won't lose anything. I already have small segmentation. So in my case, I actually still use these outputs as final output of the neural network. So CRF is only used during training. So during training, I use CRF to produce smooth version of the image. And then I say that I encourage neural network to match the segmentation mask which is produced by CRF. So I want to put this smoothness knowledge inside CRF. And what people typically do, they use this CRF after segmentation network. So they don't encourage neural network to actually produce smooth segmentation. In my case, I just this standard approach just doesn't work because I don't have full segmentation. So and I use these CRFs in this case. So I put knowledge inside. And yes, so in the end, I have basically two segmentation masks, one before CRF, one after CRF. And then I essentially minimize KL divergence between. So this distribution for every pixel here I have a distribution probability for every class, and then for every pixel, so for every pixel here I have distribution, for every pixel here I have distribution, and then I minimize average scale divergence between all pixels, between all distributions for all pixels. So just essentially it's a way of saying that these should be close.
And how do you construct, how do you perform inference in CRF with many labels? It's
So
not,
I use just standard fully connected CRF from Philip Rainbow. So with Gaussian potentials,
Okay.
and they have efficient mean field approximation to these networks. And then it's also possible to compute gradient with respect to this CRF was shown in multiple works before. Yes, so let's go back to the general picture. So what do we have? We have segmentation network which produces some segmentations. Then I have one guy here which basically provides big localization cues. So it helps network to somehow just guess where roughly objects are located. Then this guy enforces network to match some global statistics. So it says that objects which are not there shouldn't be there at all. Objects which are there should occupy some reasonable space, some reasonable fraction of the image. And then this guy snaps the segmentation towards the boundary.
So does it mean that classification losses have in its implicit bias of the data set? I mean, like, or distributions of objects in a data set?
That's right. So I have three constants here, which were inspired by previous papers, and previous papers used the same data set. And yeah, so there's some bias, and if you go for that data set, most likely you will have to tune this parameter. And I also cannot tune these parameters, so I actually may expect that if somebody does it, it should be better. But it's not clear how you can tune them because you don't have for fluent segmentation mask. You can do this on validation, but it won't be completely fair because you implicitly use a full segmentation mask to tune these parameters, so it's not completely superior.
do all losses have the same scale?
Yes, so I take care of averaging everything so they have the same scale.
Right, without any labels. So it seems like you don't need them. You can, like you said in the beginning, you can try to construct simulation masks for all classes that you have in the DBT or whatever you have, and try to show them to find like some hypotheses about what objects are on your picture.
Yeah, so I've tried just a sanity check to use standard VGJ to see like whether these big localization cues which can produce with VGJ, how good they are. So they're much worse than any out there. So they're still better than any non-big cues, but they worse than any.
I mean, this image that you have on after visualization, you can have without labels, so you can just.
Yes, but then it will be much worse. So I use labels here for visualization, so that I know actually which classes should I care about. Because if you ask this network where horse is located, it will guess that horse is also somewhere here, and then it will be, or it may hallucinate some other object. So it helps a lot to actually know which object you're looking for. Or it may be actually you may have some small object somewhere, and neural network may classify this, may not find this object. But if you say that, just imagine that there is the object there, where do you think it may be? Then actually it may guess right, even though you think that there is no object. This knowledge of which labels you have may help a lot here. You also use it inside this classification mode to enforce global statistics. And yeah, so basically use, and for global pooling, you also use them because I use different constants for objects which are not there. So basically highlighting with these labels, the blocks where actually use these labels. I think what you may try to do, you may try to use VGJ network to use these labels because it's quite good. It gives to very small 5 error and also small 1 error. So if you use VGJ to automatically increase labels, I can guess that it also won't be that bad. So
You haven't tried this?
I haven't tried this, yes. But I think it may also work.
It will be fully unsupervised.
Well, we still use million labels to train VGJ, so I'm honest. Yeah, so I think that's the last technical slide about my approach. Do you have any questions now?
Random fields needs to assign some penalties to binary penalties or binary penalties. Can you provide an expression for this penalties from CNN output?
So okay, in my series I have 2 types of penalties. One type is just unary potentials, and unary potentials are given by neural network.
Can you provide an expression for this?
Yes, so neural network for every location P, or for every location U, and for every class C, neural network puts a conditional probability, and unary potential is just logarithm. And I also have Gaussian kernels for every pair of pixels. So it's basically you have this bilateral filter. So it encourages close pixels to have to be close labels. That's the same label, and if color is also similar. Also,
Binary potentials use lightness only. The binary potentials use light.
only colors, and spatial locations. And yeah,
I could imagine that some PUC, so some probability is equal to 1 or 0. Is it possible?
It's not possible to be equal to
0.
to 0 with 1 as well, because the neural network, so this probability which is output by neural network, it's quantified using softmax function in there. And
Is it possible so the softmax function produce?
in theory, yes. In theory, no. In practice, it may happen that if you have really huge value, then effect will be 0. But if you encounter these problems, you can just add small epsilon here, and it won't be. So yeah, I think it happens in practice, and people often add this small epsilon just to avoid the error. Yeah. Okay, now I will switch to experiments. So use really short summary of my experimental setup. Use Pascal, will sit down 12 datasets for all experiments. It has 10,000 images for training, for speed analysis. It has 1,500 images for validation. And it has test set, which has roughly the same number of images, and segmentation masks are not available, so you have to submit your solution to the remote server, and then it will export them. And it has 20 semantic classes and 1 background. As a metric, so I use standard metric, which is mean intersection linear. So for those who doesn't know, it's computed on per class level. So let's say you have an image. Here is where some object section are given. Here is your prediction. So how to score this simulation? So you compute union of these 2 objects. You compute intersection, and then you basically divide intersection. So if you perfectly match the ground truth, then your score will be 1. If you are completely off, it will be 0. If you have some intersection, it will be some error.
Something like Jakarta method.
I think it's exactly just another.
do you know maybe of the methods method of measuring precision that takes into account relative importance of patches that is classified? I mean, like if you have a person, like not all of the regions of a segmentation area would be as important as I would say face or just like torso, or I mean like because I mean you can technically a lot of times maybe increase your union by just connecting like surrounding patches that technically are one object, but not like the. I don't know. Just.
But I think like this method is far from being perfect as well, but it's like much better than the method we used before, which is just average pixel accuracy, which makes much less sense. So it's not that bad, but it's also important that I think people nest the segmentation data set, which is not being used now, which is the less common. They spend a lot of time to come up with some metrics, some new metrics, and I'm not sure actually if they will not focus on detection. But it's not perfect.
Yeah, I'm just want to know maybe there's like a way to measure not just on the endpoint, but on the middle of the processing of the system.
So I thought about metrics, how well you measure the boundary.
So just like curve fitting.
So somehow you extract the boundary from the prediction, you extract the boundary, and then you measure the limit of the boundary. But then basically, it's a metric which I think it's meant to check whether you have really nice predictions.
I mean, you use 3 different measures to penalize finite system comprised of several different parts. And this looks like adding on more constraints to get better performance. But, if we measure the performance of the system as a whole, not by these penalties, but some other thing, I mean, like, it seems like there are some properties of the system that lost on the evaluation.
Yeah, I was actually thinking about it. So I noticed that in some cases I have a really nice boundary, but I don't see on my metrics that I'm much better than everybody else. I tried to find something reasonable, but I didn't really find any metrics people using. So I had some ideas, but I decided not to go for it because I didn't found anything out there, so it's too dangerous to come up with new metrics and scales. But yeah, it's a nice idea to measure some other things to get a more deep insight into problems. Yeah, so as a deep network for simulations, I use a recent paper from Chen. I still have from the team. So it's based on BGJ. It's slightly modified to be better for semantic simulation. So just modified version of BGJ. As I said, for CRF, I use Rainbow paper from me. So it's fully connected CRF on pixel level. But thanks to Gaussian potentials, you can actually do it really fast using UQ approximation. For implementing everything, I use Copy together with Python and Piano. It's actually, I think, quite convenient setup, so you can it's really fast to prototype layers in Python. And if you use Piano, then you don't have to write vector class. So you just define how for class works, and you have vector class for free from Piano, which can be against also using automatic.
So this code is published.
Not yet, but I will publish it. So all convolutional layers are computed with Copy, and only the loss function, which I just introduced, implemented by me. So it's this loss function is rather slow, but it's not a bottleneck. So so with Tiano, I haven't. So Tiano, I think is slightly slower than Kafka, like 2-3 times, I don't know. But maybe it's not good. But the biggest problem with Tiano is that it's hard to just download standard PHP network, or like lots of people who do schematation and they use Kafka for this. So I just download that and use and Kafka and adapt. And it's much easier to stay comparable with other people who use exactly the same network. So it's actually implemented in Kafka already. So you can just write the file and say the type of the layer is Python. Then you give path to a module with Python code.
So you're writing Python layers and Python layers.
So basically only write forward paths in Python using Python, and then everything else.
Because Python defines
Yes, it's relatively recent feature in Kafka, maybe more
So
than
you
1 year ago. So it's in the main version, in the main branch of Kafka.
So you're saying that you can write some function, and Fiano will compile it in C code that is interfaceable as a Kafka layer. Okay. Amazing.
So for training, I use GeForce Titan X. So it was actually quite surprised that so lots of people use Teslas now, which costs, as far as I remember, some back in time it cost about $5,000, and so they switched to it. Because I had the impression that NVIDIA just gave away lots of Teslas.
can get it from YouTube.
And now I have 2 graphic cards in our working station, and Titan is almost 10 faster. And much cheaper. And I use so I run stochastic gradient descent for 8,000 iteration with page size 15, and otherwise I use standard parameters from this paper. Okay. Here's I think my favorite slide. Results. So this table is the test set, and the last column is the proposal column, and the other columns are previous results. So it seems like the proposal column is almost 16% better than the previous results. And for completeness, I also compute the results for validation. And also, I think I'm better for every class here, and here this only for one class. Okay, so yeah, I don't have much to say about this, apart from that I think the results will be. And I have some small slides, 2 slides about some in-depth study about what's going on. So I tried to do appellation study and throw away different loss functions and see what's going on. So let's look at this column. So here I threw away the localization loss, so these big localization fields which are meant to guide the network. So as you can see, the network without this loss, it still matches global statistics. So here says, okay, there's a human, let's put it here, there's a global, let's put it here. And it doesn't really care much about the localization. So without these big localization fields, network just matches some global statistics, but it doesn't care much about location of them. It just puts them somewhere. You may also throw away classification loss. Then network doesn't really try to extend it. So here it was quite happy to find the head of the person, and then it just gave up on fitting the other parts. And here the same, like it just found 3 pieces which was not the person, and it didn't bother to try to find the full extent.
And you can also throw away smoothness loss, so you may see that the label can oscillate. Then network can extend the person, but then let's say if the profile of the phrase doesn't really snap to the and forward is also really flowy. And then if you use all functions, you may see that network tries to snap the boundary, tries to extend objects, and it also matches some global statistics that labels which should appear, they appear, labels which should not appear. And I also have some numerical results. So here it just basically images separate by hand. Of course, not in all cases my full loss function is better than everything else. So here I just wanted to illustrate typical mistakes which I expect the network to make, and I also make numerical comparison and show that with all terms you get results. And also I mentioned that I use not standard global pool, which is global weighted rank pool, and I try to train my network with just max pooling for everything or average pooling. And as expected, max pooling most of the cases underestimates the size of the object. You just need to find some small part or not full part of the object. Average pooling tends to overestimate object sizes, and then weighted rank pooling in many cases actually matches the objects much better. So of course not in all cases, there are some cases where max pooling is better, some cases everything is better. But on average I also have numerical comparison, weighted rank pooling produces the best result, and I also as a sanity check measured the fraction of foreground objects. So foreground is actually 27%. If you use average pooling, it's clear overestimation. If you use max pooling, it's clear underestimation, and weighted rank pooling is clear more or less matches. But it's actually coincidence I didn't set these parameters to match this. In this second one, just fraction of foreground. It's very simple thing to check.
Yes. During the validation,
I didn't use this for validation, so
my question would be
what is validation? So I didn't really make a validation of parameters. So I have just these three parameters which I picked up once, and I had some.
maybe give them give you a few program question, right?
Maybe, but I didn't.
Even by enabling from the documentation.
So I use validation sets to make some decisions about architecture. So when I was thinking about whether I should add this loss function or not, I use validation set to do this. So maybe I have some hidden decisions, like maybe about 5 hidden decisions based on the validation set, but I try to avoid it as much as possible. It's not completely fair. So most of the people still do it. So some people actually set up parameters based on the validation, they do quick search and then report the best result. So I tried to avoid this, but yes, when I was trying to come up with an architecture, actually most of the decisions were just decided based on visual inspection. So I had some procedure to visualize everything, and then in most of the cases you can just immediately see that something is wrong and just stop tracking.
I'm just trying to say that usually there would be some node which would decrease or increase the program function. Each of these nodes, each of these variants components in the plan to increase or decrease.
Yeah, I think you just play around with this parameter.
Like a bullet workflow for media 2, which is a video for bullet for the right creation.
So you mean you can also match this ratio with this and this?
Quite likely if one ratio with the good part of the explanation will be worse. But I didn't
But how exactly is supposed to actually?
decrease the background. Decrease the number
Okay, yeah, maybe it's also. Okay, and I think that's all I wanted to say. Maybe two take-home messages which are not directly related to this. I wanted to mention that it's not so in the beginning. I think that it's scary to implement layers for deep networks, but it's not that bad. You can do it with your favorite Python and Java. I hope it's your favorite combination. And and I want to say that it's actually when you work with deep networks, they appear to be black boxes. You just change one parameter and everything goes out of hand. This is what happens to me. It helps a lot to try to visualize as many steps as you can. So I try to visualize as many things as I can. It's not a lot. So without this, I probably would just start in the beginning with some small parameter problem. That's all. Thanks.
Also, very nice search. And then I wanted to ask, so it seems like half of the approaches for semantic implementation somehow use CRF, and half of them are using some kind of trainable algorithm.
Yeah.
And what it's a reasonable question. What is it that CRF doing? What neural network itself can do? So why do we need this extension with some drivers?
So I think so. Generally, if you have fully supervised training, I'm not convinced that you need CRF because you said there's unconventional reference which you can also train and which work quite well. I think people still use CRF on top to increase the results of this declaration network. But yeah, if you have huge data, then you can train this declaration network and there's no need for CRF. In my case, I don't actually, so I use different scenarios for CRF. So I don't have this full supervised classes. So I cannot just train network, declaration network. So I use this trick to force neural network to match what CRF thinks about the image. And then here, actually, I don't need to train anything. I already have my prior. So I need to set some parameters somehow to this CRF. It's just standard parameters, but one can also change them. So essentially, in CRF, I use some prior knowledge. And in declaration in the neural network, there's no prior knowledge to train. So they won't help you in this case because you need to train them, but you don't take it to train them. And here I don't need to train CRF. I use my prior knowledge about how images look.
So you think for supervised setup, there is no need for CRF?
This I don't see any reason to do it now. That's like how I usually started. I started from doing CRFs, and then I stopped doing them because I'm not convinced useful.
Have you tried
No, I haven't tried here because when I started this, I didn't know about
your studies?
No, I'm actually quite new to people.
So is this research accepted to some conference or something?
It's submitted a week ago to the ECC, and it's archived already, so
Oh, so we can really.
it's not inexplicable yet. I checked a few hours ago, but if you just search in the archive by keywords from the title.
Yeah. And the second one is all of the objects from natural world have like a distribution when you 3D objects are projected to 2D images from different perspectives have like the distribution of their boundaries on the 2D images. So is there in this system implicit encoding of information that some classes have some kinds of boundaries? And if it is, where are they?
I don't know. I actually have no idea what neural network blocks in Hello, so it's a black box. So, like, to some extent, I think people understand that like first layers try to extract edges, then on a high level.
But well, I know that. But I mean, positional information from which location in the pipeline is not used further away. I mean, like when you upsample the data of filters, it doesn't have any information, positional information from downsampling phases, right? Besides from filter indices. So technically, like segmentation network doesn't know anything about like continuous boundaries of things, but knows about only relative position of some responsive to filters patches.
Yeah, so essentially, it's fully convolution neural network which I use to just basically work in sliding window fashion. So you may interpret that you have some sliding window, you show like some part of the image, ask what is this, and move to the next window of what is this.
So, but Suryaev model, is it have any chance to model like distribution of boundaries, of shapes of classes? I mean, like, is there a way to extract something like we?
I hope so. Like in conclusion of my paper, I actually discussed that it's like how we can improve it further. One idea is to incorporate some additional priors. So at the moment, you may think that I use one prior by using this CRF model. So basically it's knowledge that closed pixels and closed phases. But you may also try to incorporate some additional knowledge that like images have a horizon and objects have some reasonable shapes, whatever. I think it's possible, but I don't know how to do this, so I haven't actually thought about it too much. But one possible direction to incorporate some knowledge, because it's people's words that you doesn't know much.
I mean, like masking